Hello everyone, how's everybody doing? Welcome to Rational Science. Today we're going to talk about this gentleman. His name is Juan Maldacena. He's a compatriot of mine. He's my fellow countryman. And mentioned him the other day. He's born a little farther north than me in Buenos Aires. Anyways, he works as a string theorist at the New Jersey, the Princeton Institute for Advanced Studies, IAS. Okay, and one of the things I want you to keep in mind today is, here you have the operating funds for the Institute of Advanced Study. They receive 9% of their budget from government agencies. That means taxes. You're paying maybe around 10% of their operating funds. And so one of the things you have to keep in mind is whether you want to support such a thing. And he's a practicing Catholic, okay? In fact, he received an award from the Society of Catholic Scientists. One of their goals is similar to the John Templeton Foundation's, integrate the world of science and religion. In 2018, St. Albert Award of the Society of Catholic Scientists was given to Juan Martín Maldacena in recognition of his exceptional contributions to fundamental physics. What fundamental physics? Well, we're talking about string theory. And he's won several awards for that, especially for his paper, the one he published in 1997, which has been referenced over 10,000 times. So he's a popular guy in string theory, okay? And one thing I should mention is, in comparison to the two ladies and two fellows who I covered in the last couple weeks, those are science communicators. Mr. Maldacena is a little more than just a science communicator. He's well-versed in the mathematics of string theory. So if you want to learn string theory, he's one of those top honchos that you really want to get involved with, So he's quite versed in the subject matter that he teaches, okay? That's one of the things that you have to keep in mind. So here I'm going to be analyzing one of the top honchos, okay? There's no doubt about it, okay? Okay, but I have to begin with some criticism of Mr. Maldacena, and that's because he made this comment in one of his videos. He says, if you remove the air, everything would fall in the same way. This is something that Galileo discovered. No, Galileo did not discover that, and I've covered this in the past, and I'm going to emphasize it today. Even before Galileo, Galileo was only 22 years old when this gentleman from Netherlands, his name is Simon Steven. He writes the book he publishes when Galileo was only 22 years old. The experience against Aristotle is the following. Let us take, as the very learned Mr. Groot, most industrious investigator of the secrets of nature, and myself have done, two spheres of lead, the one 10 times larger and heavier than the other, and drop them together from a height of 30 feet onto a board or something on which they give a perceptible sound. So Mr. Steven already figured out that Aristotle had a problem. He already did the experiment. He did it from the tower of the new church city in Delft. You might say, okay, but that's a close call because, if Galileo was 22, well, he could have maybe done it around the same time. Okay, certainly he didn't write about it at the same time, so Mr. Steven gets credit there. But let's go further. Galileo's replaced in 1592, he replaced as the chair of the mathematics department at the University of Padua, he replaced Mr. Giuseppe Moletti, also known as Moletto, okay? And Mr. Moletti, 10 years before Steven, now we're talking about Galileo being 12 years old, okay? Already wrote in his book the same thing, that he did the experiment, he dropped these two balls. So, and obviously Galileo knew Moletti because he replaced him at the University of Padua, and I think he was a student of Moletti as well. So he got all this stuff from Moletti in the best of cases, okay? So, no, Galileo isn't the first one. And it's a shame that all these people don't do a minimum of research before they spread these myths and just propagate it from decade to decade, from generation to generation. And likewise, we're going to go a couple more examples. One of them is that Descartes, René Descartes, the French guy, he's sometimes credited with having come up with a wave theory of light. No, never happened, never will, okay? Descartes, he didn't write, if you look at his book, you won't, especially on optics, you won't find any mention of wave or pressure for that matter. You won't find those words in there. And the fellow who wrote to him was Thomas Hobbes from England, right? And they would write back and forth. And also Thomas Hobbes wrote another treatise on optics. Neither one mentions waves. As far as I'm concerned, unless someone shows me something different, the guy who came up with the wave nature of light is Robert Hooke. He wrote a book in 1665, which he published in 1665, Micrographia, and there, no doubt about it, you'll find the word wave many times. He's the first guy who really mentions the wave, which is later taken by Christian Huygens in his treatise on light. He develops it in a more formal matter. But until then, we have to give credit to Robert Hooke. Okay? Now, one of the reasons Galileo became famous is because Newton mentions and analyzes Galileo and works using Galileo as his foundation. I don't think Newton was aware of Stevin at all. I don't know if he was or not, because you're talking about a generation earlier, quite a bit of a generation. Almost, one guy was born 100 years before the other, so there was a big difference there. Anyways, I think that all these professors, they should not propagate the myth that Galileo discovered that two different weights fall at the same time on the ground, and that he did the trick from the Tower of Pisa. No, I don't think. Maybe he did. One of his students mentions many years after that Galileo did throw a couple stones or something from the Tower of Pisa, but I don't think there's no real evidence in the writing, in written evidence that ever happened, even from Galileo or from anybody else. Okay, so we have a problem with string theory, and again, the question is whether you want to support any investigation, any study of string theory, and that's what I'm going to argue today. Okay? How do we get into string theory? Well, we have a problem with quantum mechanics, that quantum mechanics does not incorporate gravity. And in fact, there were a couple other problems. Not only gravity, we have problems in quantum mechanics understanding almost anything. As several of them. One is Mr. Bohr, the other one Mr. Feynman, even Leonard Susskind. All of them say the same thing. You cannot imagine quantum mechanics. Okay? You cannot try to make sense of it. Bohr said it. You cannot even try to illustrate it. If you try to illustrate it, well, you have a mental problem. It means you didn't understand squat. Okay? So you can't go in there and try to illustrate, not try to visualize what's happening in there under quantum mechanics. Okay? And so how do we get into that trope? I mean, if you cannot imagine, how can they say that quantum mechanics has been proven to be more or less correct if you cannot even imagine quantum mechanics? So we have something to resolve there, okay? That's all I'm saying here. And here's the problem, one of the problems in quantum mechanics, the Slit Experiment, or as Mr. Feynman says, it contains the essence of what the problems are in quantum mechanics. You have either, whether you use particles or you use waves, and you send them through two slits, you get these fringes on the wall on the other side of the partition that's got the two slits. And you would think that, if you throw particles, try to throwing balls through two slits, and you'll get paintballs or whatever, you'll get the markings, but there'll be two straight lines. You won't get fringes. You won't get many, as you see there in the picture. You won't see many lines. And with water, you can simulate water waves, but then the question there is, why do the water droplets, the H2Os, the molecules, why do they spread apart after going after the slit? Well, they push each other away. That's why they spread out, and then they interfere with each other. How do you explain that with light? Is water a good analogy for light, for photons? So that's one of the things you got to think about. The other one is entanglement. Okay, and here it is. This thing comes up there. Okay, and that's you have two particles, million miles away from each other. One goes positive, the other one instantly turns negative, or vice versa. Or one goes clockwise, the other one counterclockwise. They change colors, whatever. They take like opposite effects of each other. Their charges change, etc. And how do you do that with quantum mechanics? How can you explain that with quantum mechanics? Because what's between them? Is there a connection, a physical connection? And so quantum says, no, there is no physical connection. And what they do is use information. They say, well, the information is transferred faster than the speed of light. Yeah, when you talk about concepts, yeah, you can do that very easily. The question, can you do this with objects? And no, they can't. Quantum can't explain that with objects, with things. That's where the problem is. And the only answer that they have for that is, well, Father Universe and Mother Nature work a little different than the minds of humans. So their rationality is not the same as our rationality. And my answer to that is, well, does Father Universe and Mother Nature, does their rationality match your rationality, the one you're trying to, shove down my throat? You're saying that this is your interpretation based on your equations, and you're saying you represent Father Universe and Mother Nature, that you know exactly how they run the universe or nature, and that I'm wrong because I rely on intuition, whereas you rely on mathematics. Well, I don't know. I don't know if Mother Nature went to college and learned, trigonometry or algebra or calculus. I mean, you have two stones, the Earth and Mars, and one tugs on the other. We know that's true. It's a fact. Certainly the Earth tugs on the moon, and it's only two stones. How difficult can that be? I mean, do we have to go to college and do a lot of, integration and calculate derivatives to find out how the Earth keeps the moon faithful to it, why the moon doesn't fly out of the solar system? So these are things that, this is the focus that we're giving all this, okay? And this is the problem. The problem comes here in quantum mechanics and in mathematical physics in general. They rely on one-way waves, or they rely on one-way particles which aren't particles. The classical particle, the speck of dust, that's not what quantum has as particles. Quantum particle is a magical particle. It's a particle, first of all, that's not a particle because it's a point, a zero-dimensional point, which represents a number, a value, a magnitude, an amount. That's all that little point represents, because they can put that into an equation. See, they cannot put a tree in an equation. They cannot put a rock in an equation. They cannot put a dog in an equation. So they have to put the mass of the dog, the length of the tree, the number of seconds the clock measured instead of putting the clock. They can't put a clock in an equation. So they work with all these values that they calculated and that they measured. That's what they're going to put in there. That's their language. The question is if any of that represents the physical world from which they derived all that information. Okay? And again, these are all one-way mechanisms. What do we propose instead? Well, before that, let me just mention that as a result of that, they misconstrued the light, because, see, if you show these particles on the left going straight, how do you explain the wave nature of light with that? And if you go with the one on the right, where you see the wave nature mediated by particles, the question is what pushes each particle up and what pushes each particle back down again. Why would these particles oscillate up and down? So right now they don't have a mediator that they can use for light. Whether they use the one-way particles or the oscillating particles, or whether they use what you see on the upper left, which are just vectors. Those are just vectors. They have magnitude and direction, because they put the direction there, right? And that's all they are. And they have this mathematical concept that is moving. That's scary. Okay, but these are the things that they're going to use to give physical interpretations to their theories with. Okay, this is the issue. Okay, so as a result, they ended up with this quantum atom, which is the planetary model that Mr. Bohr and Mr. Rutherford came up with. Okay, and you can see the electron bead jumps from one energy level, as they call it, to another energy level. You can think of those as orbitals, as they also call them. Okay. And with this, they can explain, the quantum jump that you see there. They can explain ionization, and they explain electricity, which is what you see on the bottom. The electron bead moving from valence level to valence level, from atom to atom. So you ask them, okay, so electricity, according to you, is this flow of electron beads from atom to atom. Is that your atom, the one that you're using to simulate electricity? And they say, well, no, that's not our atom. The planetary model has been debunked gazillions of times. The planetary model is not the atom of quantum, but that's the one they're going to use for ionization, for the quantum jump, for electricity. So we have a contradiction, because they're supposed to use, whatever they use, they have to use it consistently, and they can't say at the end of their presentation, by the way, that talk that I just did about electricity, forget it, because the atom that I presented is not the real atom. not the one we propose. It's not the one Mother Nature uses, or Father Universe, or whoever. So we have a problem because they can't come up and start with an atom that they're going to use consistently and then not deny at the end of their presentation. That's what the problem is. What do we propose in exchange? Okay, here it is. We propose that all atoms in the universe are physically interconnected. No one in the last 400 years has proposed that atoms are physically interconnected. This is the first time we have this, 21st century. Okay, so we have a new proposal on the table, and that's that all the math that they did with discrete particles and waves, the waves maybe, but particle is irrelevant and has no bearing on physics, on light, on electricity, on magnetism, on gravity. It has no relevance whatsoever. So they did a lot of calculations, they did a lot of exercises with the integrals and with the derivatives. So what's the point of all that if they had the wrong or the irrational? Because it's not wrong, it's just irrational. You can't make sense of the particle hypothesis. Here we're saying the atoms are interconnected. There you have the 3D model and the 2D model. Okay, quantum jump, they expand and contract, and by doing so they torque the physical mediator, which is a rope-like, DNA-like mechanism, a twined pair of anti-parallel threads. There you have it. That's the model. Very simple. How is that rope and the atoms constructed? They're constructed out of the same thread. Okay, there's a single thread in all of the universe. Let's see if I can. Hope you can see that. That's. Let me put it here. Okay, there it is. That's all there is in the universe. Okay, just a single thread, closed loop thread. This thread moves around, winds around, doesn't move, but it winds around every atom in the universe, which is connected to the next atom through the electromagnetic ropes, which is made of the same thread, paired twined threads. So you go from twined threads to atom, to twined threads to atom, and so on down the line. And there's the construction on the bottom, okay, what you see. And again, I put the 3D and the 2D at the lower left. And you have one thread goes in through the center of the atom, constructs the proton. Every thread from every atom in the universe is converging upon our proton. The other one goes around and it forms this encapsulating membrane. Okay, and that's the atom that's going to pump back and forth and torque the rope. And torsion is the fastest thing imaginable. Okay, so it explains the speed of light for sure, why light is so fast, and explains a whole bunch of other features I'm going to summarize in a second here. But meanwhile, here's the difference between what mathematical physics and everybody else proposes: discrete particles, the ether, just a bunch of loose particles that have no relation to each other. They just you have a sandbox essentially, and a sandbox, supposedly all the particles move. They're like a bunch of bees instead of like a sandbox. That's the way they treat them. Under the rope model, every atom in the universe is physically connected, bound to all others. Okay, so that's the difference in the two models. We're proposing a new model altogether. And obviously, it's going to require a different set of equations, but it has no problem with equations like Maxwell's equations. No problem there. It's just when you get into this magical particles of quantum, that's when you have to look a little deeper, because there they have virtual particles popping in from the void, you know, getting together and forming nothing, and then separating, forming something, and so on. So they have all these little tricks that they use to convince you that they're right and that they're rational. Okay, so the first thing it answers is the rope model. Very easy to show to yourself. You know, you don't have to take my word for it. Proof, evidence. That's what I'm going to talk about here. You take any rope. Okay, here's a rope. Okay, and you count the links. Like there, you have 2 links. Well, you torque it some more, right? The more you torque it, the more links you have, and each link is shorter. That's the wave equation that you're seeing there. Frequency times wavelength are inversely related, so that if one goes up, the other one goes down. That's the equation of a rope. Okay? No one has figured it out in the last, 400 years, since the days of Robert Hooke and Christian Huygens. Okay, and here you can see different focus on this. Okay, and when you look at a prism, okay, you shine white light on one end, like Newton did many years ago, right? What you get on the other end is not wavelengths coming out in one direction, as they say, or particles popping out of there. No, what you have is every atom is connected to every atom in the universe, and the atoms at the edge of the prism on the right-hand side, they're connected to ropes, through ropes, to other atoms which are, I don't know, on the wall or in the air or wherever. And what you have is, as they come out of the prism, what you have is longer wavelengths on the top, lower wavelengths on the bottom. We call them link lengths, and that gives you the spectrum from red to blue and so on. Okay, so that's the model. Okay, no traveling particles, no traveling waves, especially one way. It's a two-way mechanism, so the torsion travels in both directions to both atoms simultaneously as they're pumping, torquing the rope. Okay. What does this answer? Well, for sure, what I call the checklist of light. Okay, and if quantum can do the same thing with either the wave or the particle, they should get a Nobel for it. And light is so fast because it consists of a torsion propagating along a helical DNA-like medium. That's why little c is equal to the inverse relation between frequency and wavelength, or really link length. A photon is massless because light is mediated by a tense taut rope-like pair of twined anti-parallel threads that interconnects any two atoms. The electric field runs perpendicular to the magnetic field because the twined threads on a rope can do no other. You know, just take any rope and you'll see that one runs 90 degrees to the other. In fact, when we go into magnetism, that becomes even more patently evident. A taut rope invariably embraces an imaginary axis. You can see the imaginary axis running right through a taut rope at the bottom. Light has an undulatory nature, and because of traveling transverse waves, not because of traveling transverse waves, but because the rope spinning around its axis exhibits goosebumps moving along its structurally wavy surface. You can see that at the bottom as well. And amplitude is structural property attribute of a two-strand rope. Okay, so this and several other, these are just the most common properties, attributes of a rope, but there are other features that they have shown about light that the rope handles very easily. Whereas a transverse wave, you know, it fails because what is a transverse wave? It's a flat, two-dimensional wave. It belongs to the days of Euclid. We're talking about plane waves here, okay? What is a plane wave? What physical object is that? And what they show is obviously vectors. And they have these vectors moving sideways. So they're pointing upwards and they're moving. Very scary stuff. Okay, and so how do we handle entanglement? Here you have entanglement again. One particle affects the other one at a great distance. Well, with a rope model, you have no problem with action at a distance whatsoever. Here you see them side by side. If you take one atom that's pumping torsion waves to another atom, and vice versa, right? One is clockwise, the other one is counterclockwise. As soon as you turn one around, well, the rope can only spin in one direction or the other. And one of the things that has to be analyzed here is that, you know, when no one has ever considered something like a rope mediating two atoms. And so now we have to go back and do experiments like the EPR experiment, which French guy did, can't remember, Aspect, Alain Aspect did, showing that it is a feature of quantum mechanics. In other words, that when one goes clockwise, the other one goes counterclockwise instantaneously, like if you measure here and measure there. And yeah, and the issue there is very simple. Now we have to figure out that whole experiment, again, in the context of the rope model. Are you measuring the same rope? Are you measuring a parallel rope that's moving in the opposite direction? In other words, one's moving clockwise, the other one's moving counterclockwise. See, because this is very simple. From your end, see if I can do this right, you know, I'm going to turn mine counterclockwise. Hopefully your end is turning clockwise. Now let me turn it around. Okay, now mine is going clockwise and your end should be moving counterclockwise. No mystery. No mystery under the rope model. It's a big problem in quantum mechanics. They can't explain it, and they never will with particles because they're talking about action at a distance mediated by spirits. They're back to religion. They're saying there's no physical object there between the two atoms, but one affects the other. Sounds like religion to me. Okay. And how about the Slit Experiment? Okay. Well, they do it with waves. Okay. They say there's interference. Again, they use the analogy of water waves. A lot of problems with that. But a bigger problem comes with a particle, which is the one they're trying to get through, because otherwise quantum dies, because you won't see waves in the standard model. What you'll see is particles. And so how do you do it with particles? And so they had to come up with ways of doing it with particles, okay? And so here it is in a nutshell what the issue is. You send a particle, it hits the edge of the window sill, you could say, of the slits, okay? So you have a little slit there. The photon or the electron, whichever one, however you do the test, hits the edge of that window, right? And bounces inwards. And then you can have, you can show interference from one to the other. Fine, great. In fact, here we have Mr. Tanomura. He was from Itachi. And before then, there's another claim by Mr. Gurley fellow from Italy and his group, and they claim they handled 1 electron at a time when they did this experiment. And you can see that they filmed this, and they were able to say to show that 1 electron at a time hits the screen and forms the interference fringes that you see there. And so Mr. Tanimura, like Mr. Gurley, they both concluded that obviously an electron is a particle, because it's obviously it went 1 electron at a time hitting the wall or the screen or whatever they used as a background there. And maybe Mr. Tanimura spoke a little too soon. Maybe he jumped the gun. Okay. Why? Because of this. See, here we have, again, the quantum atom. And Mr. Tanimura is assuming that electricity is what you see on the bottom, a flow of electron beads moving from atom to atom and eventually hitting the screen. And so the question is, okay, let's accept Mr. Tanimura's explanation that electron beads move from atom to atom and he handled 1 electron at a time. Is he talking about the planetary model? Is that the atom he's using by default? And he might say, well, no, that's not the quantum atom. So please show me your quantum atom before you make an unsubstantiated statement like that you handled 1 electron at a time. How do you know that electrons are beads that move around, inside the atom? Okay, so we have a different model of the electron, and yes, when we apply Schrodinger's equation to our atom, it's a little different. It's not a little bead that's over here and over there. No, the electron is a membrane, and what Schrodinger's equation does is not tell you where you can find the electron bead. It tells you a location on the membrane. It's a different model, and we use the same equation, but it has a different meaning because it's in the context of a membrane, which is what chemistry uses anyways when they do, molecular bonding and so on. Okay, so keep that in mind. Okay, here's the other problem that Mr. Tanimura would run into in all quantum mechanics, because what they cannot explain is this, and that's that what if we remove the partition, the slit partition, and replace it with a needle? We're going to replace it with a little needle. Okay, see that? Okay, so we're going to use the needle. I don't know, maybe you can see it better there. Okay, we're going to use a needle, and we're going to shine. I'll do it with a light because you can see that. Okay, but let me get this one out of here for a second. So see if I can do that. Okay, you see the laser pointer. Okay, laser beam, and if I point the laser beam at the needle, I will also get fringes on the wall. In fact, I did the experiment. You can find it in one of my videos there. I did it live. And so what's the issue there? The issue there is that what Mr. Tanimura and his colleagues will not be able to explain essentially is this. If I can get this thing up here. Okay. If we remove the partition, put a needle, now what will the photons or electrons bounce against? See, there it's bouncing. But if we remove that, okay, now the electron or the photon has nothing to bounce against and won't come inwards to interfere. Indeed, first let me show you this. Here we have a tree, okay, and you shoot 2 balls, right, and they're going to interfere with each other. But the one on the right, should hit the tree and move outwards, okay? There's no way that ball can hit the edge of the tree and move inwards, which is what quantum is saying is happening, and because they have to interfere like this, see? So this is what quantum, where quantum uses this magic. It says, well, it turns the corner, like the water waves that turn the corner. Well, so does the particle. What justification is that? How does that particle hit the edge of the screen and of the slit and move towards the left, for example, in this case, right? Okay, so this is the problem. And in fact, Mr. Tanimura, in his diagram, shows it. Look, here he shows that he did it with electrons, okay? And what happens? He sends the electrons, but he needs an electron biprism to get the beam to converge. Otherwise, if he doesn't have that electron biprism, then what happens, those lines will go straight and you won't have interference. So whether you use particles or like electrons, if you use tennis balls, like he did here, you have to have something that pushes them back in. And that's where he uses the electron biprism to focus the beam back in so he can create the interference fringes. Then he claims that he handled 1 electron at a time. No, the way he would have shown that he handles one electron at a time is get rid of the biprism, the electron biprism, and just do it with electrons. See if it works then. No, the electron beads well, they won't go around. They'll just keep going, and he knows that. That's why they use the biprism. Okay, so yeah, again, Mr. Tanimura jumped the gun, and this is why he jumped the gun, because he did it with a gun. He thought he was shooting bullets, and the way we explain it is like a drill bit. We can make holes in the walls also with drills. So we have a different mechanism. It's not shooting bullets, it's drilling. Okay? And for this, you need to know what electricity is. Okay? Because this is the problem. These people say, well, electricity is the flow of beads. Well, how do you know it's the flow of beads? How did you prove that? Or is it just that you inherit that stuff from classical mechanics in the 19th century? Okay, so here's the slit experiment according to the rope model. What you have is you turn on the light, and when you do, all atoms in the needle are connected, already connected to all atoms on the screen. And in fact, they are connected before you turn the light on. Everything is already connected with ropes, electromagnetic ropes in the universe. Every atom is connected to all others. When you turn on the light, what you're doing is increasing the frequency of the rope of the, what you're doing is, again, what I showed earlier. You're increasing the torque. You have more frequency, in other words, more links, and each link is shorter. That takes what was until then dark, it takes it into the visible range. And now as soon as you have it in the visible range, it relays that signal along the ropes that are connected from the needle to the partition. Everything is connected. All you're doing is turning on something that's already there. Okay? And then, yes, you can create very simply the interference fringes simply by following what has been known so far as wave interference, both constructive and destructive. So all you have to do is apply the wave notion that they did, but you apply it to the rope, and we're done. There's no change there. What we're changing is the mediator. We're saying it's a three-dimensional, not a two-dimensional wave fields, which are concepts. No, which are numbers. What's a field? A field is a bunch of numbers. That's all a field is. There's no physical object called a field. Here we're talking about a physical object. We're talking about a rope. So some people say, well, Bill, all you did was replace the word field with the word thread. No. Thread is not a field. Field is a concept. Thread is a physical object. Okay, and that's where people have to learn the language. Okay. So here's just a brief last issue here. I'm going to compare the electricity of quantum mechanics and classical mechanics against the rope model. Classical and quantum mechanics, they have these beads flowing from atom to atom. Under the rope model, what we have is a torsion of what we call a serpentine. All these atoms or molecules, depending on the context, are physically merged one with the other. They form a long string and they rotate in situ. So when you turn on the electricity, all you're doing is twirling something in there. It's rotating around the axis. It's spinning around the axis. And here's the circuit comparison also between the rope model and the quantum model. Okay, so the quantum says, look, when you bring down the switch and you create a connection there, a closed circuit, what you have is electron beads flowing, and that's what everybody learns out there. Okay, 21st century, we changed all that. We're saying, okay, now if you look at the bottom right, that's an iron atom. Okay, so we have an atom there, and that atom we're going to join up with all other atoms. There's your atom. Okay, we're going to merge them. They're going to blend with all other atoms. Okay, and we're going to form a long thread or wire of iron. Okay, that's going to be our model. That's what's inside your cables. We're going to assume it's all iron, okay, just for the ease of explanation of the mechanism. And then what's going to happen, that iron, all those iron molecules that are stretched out in this long string, they spin in situ. And so when you bring down the switch and create a closed circuit, what you're doing is torquing the entire snake that's rolling around from head to tail, okay? And of course, it goes in both directions. So that's why there is no delay. The one end of the circuit is not waiting for the little ball to reach there and say, well, when is that ball going to reach here? No, in the case of the rope model, the snake turns inside out, or, it turns on itself from beginning to end, from head to toe, and from toe to head in both directions. Okay, so there's no delay. Okay, so you can see the differences between that and quantum mechanics, what we propose. What's the issue? The issue is when we come to gravity, because quantum has no explanation for gravity at all. Okay, The gravity theory is general relativity, and not special, by the way. Special relativity is gravity-less. It's a flat universe, flat world, okay, a flat land, okay. There's no gravity. You can't fall down in flat land, okay. You can only fall sideways. So there's no gravity in flat land. So when we're talking about gravity, we're talking about general relativity, okay. But what you have is that quantum mechanics has no explanation for gravity, okay. And so what you'll see out there is the following. You'll see the standard model. The standard model looks like this. And sometimes, you know, they put the graviton, which is the particle of gravity that mediates the gravitational force, but they say it's a hypothetical particle, hypothetical graviton. And most standard models don't even include it because they don't want to embarrass themselves. They say, well, here we are all these years, we still haven't found the graviton. Okay, they found the Higgs with the particle of mass. They found all the others, but they can't figure out, you know, how this graviton particle works. What does it do? What's its purpose? And let me tell you what the problem is there again. And it's more or less like this. This is the explanation, okay, or the objection to the graviton. The standard model is inherently an incomplete theory. Okay, they concede this. There are fun, and remember, Niels Bohr said it was a complete theory. So did Heisenberg. These people are saying today, well, not true. Einstein was right. It's not a complete theory, which is what Einstein was criticizing about, you know, quantum mechanics. That it wrote a paper in 1935 saying it's an incomplete theory. There are fundamental physical phenomena in nature that the standard model does not adequately explain. Gravity, first one on the list. The standard model does not explain gravity. Straightforward, period, we're done. The approach of simply adding a graviton to the standard model does not recreate what is observed experimentally without other modifications. Moreover, the standard model is widely considered to be incompatible with the most successful theory of gravity today, general relativity. Okay, so that in a nutshell tells you something about gravity as far as quantum mechanics is concerned. It has no answer to gravity. Okay, so what do they do in, just so you can see one of the big problems that they have in quantum mechanics. Here you have a Feynman diagram, and you can take time forward, or like they do in quantum physics, they take time backwards. What they have is two electrons, they're moving, and they throw a photon at each other, or one throws it at the other, because it can only go one way. Remember, all these waves and particles, they only move one way. But that's how they interact. And so they say, look, if you have two electrons, they're moving parallel to each other or more or less parallel, and one throws a photon on the other, it'll move that one away. Okay, we all understand it because it's a push force. Now, how do we do pull? Okay, that's where we have a little bit of problem, okay? And here you have what string theory proposes for the graviton. It says, look, it's one of these closed loops strings that forms what we call the graviton. So the graviton is really a particle, but it's made out of vibrating one-dimensional strings. Okay, fine, no problem. Please explain with your graviton, your string-like graviton, please explain pull. I want you to explain the only force that mathematical physics to this date has been unable to explain, and that is the force of pull. So, you know, all these mathematical physics, whether you talk about gravity, general relativity or quantum mechanics, you're always talking about push. It's all pressure. It's all, it's all pushing. There is no pull. So half the forces of the universe are missing in mathematical physics. And they've been missing for 10,000 years because what they can never explain with discrete particles is pull. Even in the case of general relativity, where you have, you know, the depression in the space-time canvas, the fishnet, trampoline, whatever you want to call it. When you have that depression, why does the ball fall down? Why doesn't it fall upwards? And you say, well, it follows the contour of space-time. But then you're introducing gravity. You're saying it falls because of gravity. Why don't they make the canvas upward so that people are aware of that? See, if they made it, if they always drew it upwards, then people will say, oh, that's counterintuitive. You mean, here's this ball rolling. I can understand it going down into the hole at the bottom. But now you put the hole in reverse and the hole is upwards. You know, like imagine a hole inside a mountain. Do balls travel up that hole? I mean, if you make a hole in the ground, yeah, you can play golf. The ball will fall in the hole. But hopefully you don't have a field where all the holes are in the ceiling and you play golf and try to get the ball to fall inside the hole. You know, you're standing upside down with your feet magnetized against the ceiling, and you hit the ball. It's always going to fall down. It's never going to fall into the hole. And so this is the issue. What they cannot explain is the force of pull, even in general relativity, no matter how they twist and turn it. So all they can do is treat it mathematically. Okay, and this is the issue. The issue is they're just going to do math. Okay, so one of the things that they tried to do was to incorporate gravity from general relativity, blend it somehow with gravity in quantum mechanics, which has never been defined. Okay, they don't have a mechanism for gravity in quantum mechanics, but they say, look, we have this graviton particle, and maybe somehow we can merge these two theories, general relativity and quantum mechanics, find some commonality, not in physics, in mathematics. They're going to do equations. They're going to try to equate the equations, or somehow figure out how the equation of one discipline matches the equations of another discipline. That's what string theory is all about. They're going to try to get these equations to somehow be compatible with each other. Okay, so what is and what the best way to do it with is with a black hole, because the black hole of general relativity is a good place where you can start playing with particles. Remember, you have a singularity at the center. Well, that sounds pretty much like a point particle, which is also zero-dimensional nothing. Okay, and then what happens to particles that fall into the black hole? For example, in Stephen Hawking demonstrated that you have this Hawking radiation, particles coming out of the black hole, which supposedly nothing comes out of a black hole. Well, Stephen Hawking says you're wrong. They do. He proved it. Okay, so they have these particles coming out of the black hole and going in, and there's this thing going on at the edge of the black hole, and they say, okay, maybe by studying that, we can get an idea of how gravity can be merged from quantum mechanics can be merged with gravity from general relativity. That's the idea of string theory. That's the overall structure or the goal or the foundation of string theory. Okay, so what do we get from Mr. Hawking? Well, he says the horizon is a boundary defined by light like geodesics. Okay, it is those light rays that are just barely unable to escape. If neighboring geodesics start moving towards each other, they eventually collide, at which point their extension is inside the black hole. These things extend inside the black hole, the geodesics. Okay, that's what a black hole is made out of, according to these people. So the geodesics are always moving apart, and the number of geodesics which generate the boundary, the area of the horizon, the event horizon, right, always increases. Okay, as more junk falls in, you know, you have this event horizon which expands. Why? Because you have more mass, and the radius of the event horizon is a function of how much mass the black hole has. Okay, that's essentially the notion here. Okay, and Hawking's result was called the second law of black hole thermodynamics. Okay, because they're going to be saying the following. They're going to say that if a particle falls into a black hole, well, what happens to the particle? Well, the particle disappears. It gets crushed out of existence. The matter of the particle gets crushed out of existence, but not the information. The information still remains floating around inside the black hole, whatever that means to you. Okay, in other words, the charge, the mass, all this stuff is still floating around in there. The momentum, right? All this is still inside the black hole in the volume constrained by the event horizon, which is this membrane, for lack of a different word, that somehow encapsulates the singularity. Okay, so you have a singularity in the center. You have this region of influence, which is like a campfire. You know, you can get close to the campfire. It's too hot. You can, farther you go out, well, the less heat you get. And that region of influence, that region of heat, that's what's going to be called the event horizon. Yeah, the boundary. And any particle that falls in there, the particle gets crushed out of existence, but the information remains. And you say, well, who cares, Bill, if, you know, I can't see it because I can't peer inside the black hole. I don't know what's going on inside there. So it's like, okay, but they say that you can determine all that information that is floating in there for that particle is mapped at the surface of the black hole. It's mapped. It's represented at the event horizon. So you have a 2D surface, as they call it, you know, which is this event horizon, a perfect sphere, you would think, right? And it contains the information of the volume that it encapsulates. That's why it's called, that's why they've gone into holographic universe, and that's why they talk about holograms in the context of black holes and string theory. the holographic notion, principle, and universe, all that has a lot to do with string theory, because they say, look, if we can find a relation between the surface and the volume, if the mapping of the volume is on the surface, right? If you can map it on the surface, if you can represent it at the surface by studying the surface, you can tell what's going on inside a black hole without having to travel into one. Okay, so that's why all these blackboard guys go in there and play around with the equations. They figure out integrals and they calculate derivatives. Why? Because they're toying around with what happens to a particle when it falls back and forth, because some particles come out, some particles go in. So they analyze all these parameters and they play around with the equations. Okay, so it developed a cottage industry for the new wave of mathematicians, because they say, look, in quantum we're at a dead end. We found a wall. We can't go further in quantum because, like Mr. Bohr said, it's a complete theory, as complete as it can be, and it's not complete. So what's missing? Well, we need to get gravity, and gravity is outside the bounds of quantum, so we have to move into string theory to analyze it. Are they going to give you a physical interpretation? No, they're going to give you a mathematical interpretation. They're trying to unify the equations, because they say this one describes gravity in general relativity, and this other one describes string theory, right? Describes gravity at the quantum level. Okay, but for that you have to consider not zero-dimensional points. You have to consider one-dimensional strings. Okay, so now that's where the change came in. Started in around 1970s, the late 60s, beginning of the 70s, and that's been 50 years. And so this thing has been ballooning ever since. And part of it is because the new breeds coming, into college, what else are they going to do? Well, they're going to play with the math related to black holes, particles at the edge of a black hole. What is a black hole? Well, black hole is all gravity. That's all a black hole deals with: gravity and mass and gravity. That's 99.99% of what a black hole is. So if that's been proven, and they've seen them out there in the sky with their telescopes, et cetera, and they took pictures of them, right? Won the Nobel Prize a couple years ago, then that's where you got to go. You got to go inside the black hole and study particles in there. And what do? You play around with the math, and it gives you, gives you something to do in your spare time. Okay, so what are they saying? What is gravity according to general relativity? Well, here I'll give you an analogy, okay? And it's, imagine that you see the Earth. The Earth has all these parallels and meridians. Well, the meridians meet at the North Pole, right? Because they get curved, and they get curved inwards on a globe. Okay, so what happens if we put two elephants, right? And we run them along these, what they call geodesics? Well, they're going to crash at some point. They're going to bump into each other as they approach the North Pole. It's obvious, right? Because their paths are curved, and so they're going to meet each other whether they like it or not. They're going to, they're going to touch each other. And here comes the astounding conclusion of the mathematicians. They said that's gravity. The reason the elephants came together is because of gravity. What's gravity? It's geodesics, curved geodesics, which do not run parallel all the way to infinity. They meet. They meet because the surface that you're analyzing of whatever object, that celestial object, is spherical. It's curved. So if it's curved, the geodesics point inwards, they touch, and whatever runs along those geodesics comes together. And let me give you an analogy. Maybe it'll help you visualize this. Okay, see if this makes sense to you. Your friend and you, he starts from his house, you start from your house, and you go along the paths. He goes through the forest, you go through the city, right? It turns out your paths are curved, and they meet at the waterfall. And it turns out, yeah, when you both reach the waterfall, you meet the other guy, and you bump into him and say, hey, Joe, you're here, huh? Did you get closer to your friend, to Joe? Did you get closer to him because there's a gravitational attraction, or because the paths are curved? That's what these people are saying. These people are saying that it's geodesics tells you that space is curved, and that explains gravity because you come closer to the other fellow. Because, the geodesics, the curved itineraries, they meet on a curved surface. That's their argument. And here, let me rub that in a little bit. You got a little GIF here. Let's remove one of the elephants. Okay, and this time we have only one elephant. Okay, and he's going to run all by himself on a geodesic. Now, is he approaching the other geodesic because the path is curved? I mean, is he being attracted by the geodesic by an itinerary? Is this what we should conclude here? You see what's happening? The elephant is coming closer to the other geodesic. We got rid of the other elephant. There's no matter. All we have is an itinerary. It's he approaches the other itinerary. What pulled him there? Is it just the fact that the two itineraries are curved? In fact, I could remove all the elephants out of there, and the question is whether, two itineraries that meet represent gravitational attraction. This is what these people are saying. They're into such abstractions that you wouldn't believe. And they can do this because they just do math. When you ask them for the physical interpretation, they say, oh, I'll go to the other side of campus to the philosophers of science. They do that stuff. So why did they try to give a physical interpretation to their equations if that's philosophy? Why do they do philosophy and mathematical physics? And I'll tell you why, because otherwise their math is irrelevant. Because if they cannot provide a physical mechanism for how this universe works, their math is irrelevant. So they have to extrapolate it into physics and say, well, this is the description we've got, and obviously, all these geodesics meet, and that's gravity, because the equation says so. So it's gravity is two itineraries that attract each other, or that somehow meet, or whatever. Okay, what happens with a particle? Because we have to unite particles from quantum mechanics with general relativity's geodesics, right? So what happens when a particle falls into a black hole? Okay, so got the wrong one. Hold it. I think I got the wrong one. Or did I get the right one? No, I got the right one. Okay, so you have the particle fall into the black hole, okay? And what happens there? What happens is that projection is onto the surface of the black hole, okay? So even though the particle disappeared from a structural point of view, its ghost, its spirit remains, and it's reflected onto the surface. So the surface carries the information of the particle that was annihilated by falling into the black hole, okay? So all you have to do is study all the particles that form the horizon, the event horizon, the boundary of the black hole, okay? That's all you need to study. And how do you study them? Well, you do equations, you do integrals, you do derivatives. Again, the cottage industry has developed around this, and people have a lot of work to do because there's a lot of stuff to calculate there. And so they're all into this world. They're not worried about the physical interpretation. They're just worried about getting the math right. They want the equation that gives them the gut, the grand unified theory, or the toe, the theory of everything. What is a theory? Theory is an explanation, not in math phys. In mathematical physics, a theory is a description, a mathematical description. Explanations, that's on the other side of campus. So when people, nobody cares about math, so people just say, well, tell me what gravity is. And they say, well, you got to take math to understand it. Okay, so that's the answer you get. Okay, so what did Mr. I was thinking of Maradona. What did Mr. Maldacena come up with? What did he provide to this? Well, first let me look at this. Here you can see that each patch on the surface of a black hole, you can take a Planck area, which is a very tiny, the tiniest thing you can imagine, so to speak. Okay, and you have, what do they talk about? They talk about these areas representing entropy, representing information, and this sort of thing. They say the entropy of a black hole is proportional to the number of Planck areas that it would take to cover the black hole's event horizon. Okay, and so again, what did Mr. Maldacena contribute to this? If I can find it here. Let me get this thing up here. Okay, and this is his conjecture essentially. Okay, and it has to do again with equations. It has to do with just calculating things. It doesn't have anything really to do with the physicality. He's not going to give you a physical interpretation. He's just going to give you a mathematical description. And essentially what he's saying is, that the math that describes the behavior of particles that interact weakly, on the surface of a black hole, more or less approximates the math of a strongly interacting particles described in quantum field theory. Okay, so essentially this is his argument. This is what he contributed, and this created a can of worms that the mathematicians are still trying to elucidate. Okay, so this is what his contribution is. For this, he won a lot of those prizes and so on. Okay, and so it gives you this holographic black hole, so to speak. Okay, which looks more or less like this, says that the surface essentially contains the information that's inside the black hole. That's it. Now, why don't I go in more detail in all this? I mean, first, because I spend all year on it. But more importantly than that, it's irrelevant. All of this is irrelevant. It has nothing to do with physics, nothing to do with science. And that's why I'm suggesting that you consider very well what your taxes are used for, especially in relation to the IAS, the Institute of Advanced Study. Okay? And let me tell you why it's irrelevant, because there's no physicality to this. It's all abstraction. Let's see what the rope model proposes first for gravity, okay? So that you have something to compare it against. And here's a simple Mother Nature's universe, very simple. All atoms are interconnected. So we have a cylinder and we have 6 atoms on a cube, 1 atom on the cylinder. You can see what's happening here as the distance between them decreases. In other words, if you apply Newton's equation, which is tested quite thoroughly here on Earth at least, okay? As the cylinder approaches the cube, what you see is the ropes that interconnect all those atoms, they fan out. That's it. That's how simple Mother Nature is and how she does her daily work of gravity. And there you see when they're farther apart, okay, there is no action at a distance that you just cannot see the mediator or touch it, okay, and I'll get to that in a second. But when they're farther apart, okay, gravity is weak. Why? Because all the, you're pulling almost on a single coaxial. All the ropes come together and they, at great distances, like one star from another. The only reason you see only a little dot in the sky is all those ropes have become, come together and formed a single coaxial. What happens when 2 objects approach each other, like, maybe a comet approaches the Earth or an asteroid or whatever? Well, then you get the what you see in the second group there. The ropes fan out. Closer they are, the more the ropes fan out. And yeah, that explains gravity. That explains the acceleration of gravity. Here you have another version of that. Okay, just so that you are familiar with the mechanism that we're proposing. Here's an astronaut falling to Earth. And the closer he gets, the more the ropes, every atom in his body is connected to every atom on Earth. I didn't draw them all, by the way. And as he falls, okay, the ropes fan out. For every location that he has with respect to the center of the Earth, he has a different weight. You have relativists who tell you that if the sun were to disappear, it would take 8 minutes for us to find out, because nothing can travel faster than light, and light takes 8 minutes to reach us from the sun. So gravity cannot travel faster than light. So if the sun were to disappear, like Zeus or God or the devil made it disappear, you wouldn't find out about it until 8 minutes later. Well, that's impossible, because it violates everything we know that we've confirmed out there. And that is that you have weight for every step you take. An astronaut has weight for every step he takes in the direction of the Earth. So for every location, he's got a different weight. He just has to move 1 millimeter forward, he's already got a different weight. How can you explain that? Well, with the rope model, you can explain it, because now the number of ropes is different instantly. As soon as you move to that new location, you have a new set of ropes. Why? Because they were all on the same axis. Now they suddenly separate, and then they separate some more, and then they separate some more. And the ropes in between keep getting out of alignment. They're not on the same axis. So you have more effective ropes, as we call them. And that explains not only the acceleration of gravity, it explains why if the sun, if God came in there and made the sun disappear, you would fly out of there instantaneously, just like if you're climbing a mountain and you're hanging from a guy, he's up there and you're hanging, he cuts the rope, it doesn't take 8 minutes for you to receive the information. You will fall instantaneously. That's how it works with a rope model. Okay. So why does the Earth go around the sun? Something that General Relativity cannot explain. Why can't they explain it? Because they use space-time. Space-time is a concept. We have to explain why the Earth doesn't fly out of the solar system. Are they saying there's a warp time that comes in contact with the skin of the Earth? That's why the Earth cannot fly out, because there's a warp wall of time. Under the rope model, very simple, the sun twirls the Earth around from the ropes. Every atom in the Earth is connected to every atom that forms the sun. And what happens is that space is nothing, absolutely nothing, meaning it has no shape. That's the definition of space, of vacuum, that which has no shape. And so there's nothing there as far as space is concerned, so the Earth has nothing to rub its elbow against. There is no friction between Earth and space. And so, yeah, there's nothing to stop the Earth from floating around the sun forever. There's obviously some changes gravitational changes in the sense that there are other planets that are pulling on the Earth. The moon also pulls. There's a rotation. There's lots of movement in there, and that also makes sure that the Earth doesn't fly forever around the sun in the same way. Sometimes it changes its magnetic field. Sometimes it might change its orientation, given millions of years, etc., etc. Okay. Okay, and so why haven't they discovered? What's the problem with this? People say, well, I've got a problem with your rope hypothesis. They call it theory. You know, it's a hypothesis. Okay, it's known as a hypothesis. What is a hypothesis? An assumption. Okay, so you make an assumption, and with that assumption, you explain a mechanism. That's what a hypothesis is. So what happens? Some people say, well, I can't see the rope. You know, when I drop a pencil, here I'm going to drop this. Okay, okay. When I let go of it, it falls to the floor. And we know that. You can do the experiment at home, always in the presence of a trained relativist. And if you let go of a pencil, a pen, a spoon, the baby, whatever, always falls to the floor. Okay? No exceptions, unless there's some other factor out there, you know, influencing your experiment. Otherwise, it falls to the floor. And the question is, you know, when you look at this, you say, well, I don't see anything. I can't touch anything other than the air, right? I don't see anything here. In fact, you can do this in a vacuum. It'll do the same thing, like they did it on the moon, you know, feather with a hammer. Okay, so there's nothing there. And you say, so Bill, where's this famous rope of yours when we need it? Okay, and so let's bring Mr. Al-Khalili, Jim Al-Khalili, which we talked about a couple of weeks ago. And he says the following. He says, you put this guy over here. He says the following. He says, imagine I'm the sun and this tennis ball is the earth in orbit around me. Okay, Newton's laws can describe very precisely the path the Earth takes around the sun in terms of the mutual gravitational attraction between two bodies. Okay, great. But what Newton can't explain, okay, what Newton can't explain is what connects them. He's looking for a connection, physical connection. In reality, of course, there is no invisible string between the Earth and the sun holding the two together. There's just empty space, a complete void. And yet, according to Newton, the Earth and the sun pull on each other instantaneously across a vast distance. How can gravity act in this way when there's nothing to connect it or transmit it? So how did Mr. Al-Khalili and his colleagues, how did they conclude that there is nothing binding the Earth with the sun? Where did they get this? And where does everybody get this idea? Well, you know, I can't touch or see anything between the pencil and the floor, so there's obviously nothing there. This is what prevented all these people from visualizing the mechanism, and it's prevented people from ever discovering the rope model of light, okay, and gravity. And so we have to start at the beginning, and a good place to start is with the foundations of physics. Physics cannot be done without an object. It's called the golden principle of physics, started in the 21st century. Golden principle says you can't do physics without an object. If you erase all matter from the universe, there's nothing there. No shapes, okay, nothing there. No structure, nothing. Then what is happening? What are you visualizing? What can you measure? What physics is there without objects? So the first principle, the golden principle, is that you need an object to do physics. And the next step is to define what an object is for the purposes of physics. All these people have said, well, what an object is see and touch. Whatever you can see, whatever you can touch. So they say, well, let's go to the lab, let's see what we can see, let's see what we can touch. And it turns out they can't see or touch the mediator of light, the mediator of gravity, the mediator of magnetism. They can't touch or see any of those. So they never learned the lesson after 10,000 years. And so we have to put this up here. Okay, here it is. Okay. What is an object? An object is that which has shape, not that which you can see or touch. You can't see the air, but hopefully the air is made out of atoms, molecules, right? Is an atom an object? I think a lot of people would say it is. It's an object. You know, you might talk about subatomic particles, but hopefully an atom that people say is an object. In fact, under string theory, all particles are black holes. Yeah, just like you heard. Particle is a black hole. And when you look at the surface of a say a proton, what you're looking at is the surface of the black hole contained within it. In other words, you're looking at the at the surface of the event horizon of the proton, and the volume contains the information of the volume that's inside that membrane or that whatever that perimeter. Yeah, so every particle is a black hole. That's another reason string theory likes this stuff, because they can now talk about black holes and in the context of particles. Okay, you see where this has gone. Anyways, the point here is that you can't touch a tribar because there's no such monster. You can touch the paper, you can touch the ink, maybe the pixel on the screen, but you certainly cannot touch a tribar or a circle or any of those. You can't touch Snow White. You can touch the ink or the paint or whatever, but you can't touch Snow White. And likewise, you can't see the air. Okay, so are those not objects? No, they're objects because they have shape. Two-dimensional objects are objects. Three-dimensional objects are objects because they have shape. They all have shape. They have the universal property that all objects have, which is shape. Once you define it as shape, well, then a lot of people have a lot of problems because now you a lot of things like space-time, zero-dimensional particles, black holes, zero-dimensional black holes, which are surrounded by the concept known as event horizon, which is the region of influence of a singularity, which is a concept. All that is washed away. There is no such thing as a black hole. And that's why string theory is just spinning its wheels, because all they're doing is analyzing stuff that has no reality whatsoever or has any possibility of being, primarily because they never defined the qualitative terms necessary to begin their investigation. They can do the math, but based on something that's real. But when they develop integrals and calculate derivatives on stuff that has no chance whatsoever of having any reality, any existence, any actuality, then what are they doing? They're spinning their wheels. And that's what you're paying for when your tax dollars end up at the IAS. Okay, dark matter, the last one here, just so we finish up. They can't answer what dark matter is. They're investigating this dark matter thingy, okay? So what is dark matter? Very quickly, when you have a galaxy that rotates, okay, what they found is that most, if not all, I think, at least most spiral galaxies, the stars on the outside, on the perimeter of the galaxy, move just as fast or faster than the stars on the inside. That's what that graph shows there, okay? So you can see there's a curve that goes downwards, another curve that goes upwards. The one that goes upwards is the one they verified. The other one is the one they calculated. But then calculation doesn't match reality, so they said, okay, why doesn't it match? And they fixed it. They fixed everything like they do every time. They fix it only through mass and gravity. That's the only thing a mathematician understands. He only understands mass and gravity. So they said, well, what if we sprinkle all these kilograms over here? Well, yeah, then you can make an ad hoc solution to this by saying, well, if we add all this mass out here on the outside, I don't know why all this dark stuff is on the outside, but they just put it on the outside by hand. And they said, well, if we put all these kilograms here, then we can explain why a galaxy rotates like this. It's called the gravity rotational problem. Okay, so they fixed the problem artificially by putting kilograms there. Great. And so now they're looking for these dark kilograms, these invisible dark concepts. And they're trying to reproduce them at the LHC, at the Large Hadron Collider here in Geneva, okay? And so, yeah, a little bit of a problem, because if there is no such thing as dark matter, which they claim they have proven already to exist, if there is no such thing as dark matter, then all the equations, all the work that they're doing at the LHC to find dark matter, all that work is in vain. These people are working on stuff that has no reality whatsoever. They're in left field working who knows in what. So how do we explain it under the rope model? Very easy. It's baby stuff. It's for kindergartners. So I don't want to offend your intelligence by showing you this, but Mother Nature is a very simple woman. She only deals with rocks. I mean, what is a planet? A rock. What is Mars? That's a rock. And so when you have two rocks like, I don't know, Mars and one of its moons, Phobos or Deimos, you only have two stones. How difficult can it be? Do we need to know trigonometry for this? Do we need to know geometry for this? So no, the way it works is that when a galaxy rotates, okay, all atoms are interconnected, means all stars are physically interconnected. So a galaxy rotates like a carousel, like, the stars on the outside rotate more or less at the same speed of the ones on the inside, maybe faster, maybe slower for different reasons, because they're also tugged by other stars. But the point here is that if you have a physical connection between all stars, now you can explain why a galaxy rotates almost as a single piece, as if it were a disk. Okay, so it's very simple. We have to get rid of this dark matter nonsense and simply concentrate on the physicality, on the fact that all atoms are interconnected. Then it's a piece of cake. Then you don't have to ponder about what I explained the other day, MOND, the modified Newtonian, the equation for MOND, or dark matter. You don't need any of that, because all those are mathematical fixes. They're ad hoc fixes to make the equations match what they see out there. That's how they proved the existence of dark matter. They simply put in a factor in their variable to make the equations match observation. That's what they did. And we don't need any of that. All we need to say is, look, let's make it a qualitative assumption. All atoms are interconnected, physically interconnected, meaning all stars are physically interconnected, and then the whole thing rotates like a single carousel. We're done. That's how simple it is. That's how simple it was all these years. And these people can keep doing math all the way to kingdom come, you know. Okay, just some of the comments from people who do not agree with Mr. Maldacena and his string theorists. Okay, here's probably the first vocal person. His name is Sheldon Glashow. He's a Nobel Prize winner. And he says Glashow is one of the remaining phenomenologists at Harvard. Phenomenologist is a person who wants to use his hands and eyes. He believes in experiments. Okay, he said, what experiment can you run with string theory? That's his main objection to it. And he says string theory is a discipline distinct from physics. He puts it outside the bounds of physics. You may call it a tumor, if you will. Absolutely love that. String theory is a tumor. But he continues, and he tells you why string theory is dangerous and maybe why you should not contribute to the IAS. And here's his comment. He says the following. He says, the LHE is smashing particles to discover the nature of the subatomic world. Who will be interested in trying to fit these discoveries into the theory? It will be people like me, except we may be dead by then, or if not, we'll be rather old. Or it will be the young theoretical physicists, but the young theoretical physicists are doing string theory, and they ain't interested in the results of the experiments. Not now and not then. So who's going to be there to continue the role of building a better theory of particle physics? And yeah, I feel for Mr. Glashow, because he sees that all the work of all these accelerators is going down the drain because these folks are staying in their little houses doing maybe home office, and all they're doing is calculations. And their calculations are just to figure out what the relationship is between particles and a black hole, meaning string theory. That's where all the effort is going. You're having more and more string theorists today. Why? Because they've given up on quantum mechanics, on the explanations that quantum mechanics has not addressed. And they feel, they have this sense, this intuition that string theory is the way to go. That's because you have to somehow unite these two disciplines, general relativity and quantum mechanics. And you can't do it with one or the other. You need both to get the gut, the toe. Okay? And he's not the only one who complains. There's another vocal individual against string theorists, just so you keep these people in mind. This is Mr. Peter Woit, I think his name is pronounced. Valuing, what's his complaint? He wrote a book, Not Even Wrong. And no, I didn't turn the book around. That is the cover of the book. Valuing mathematical elegance over empirical evidence. He says you need empiricism. Lacks testable predictions and is promoted with public money despite its failure so far. Okay, so again, where are you going to put your dollars? You're going to put them in string theory. You're going to support the IAS, the Institute of Advanced Study in Princeton, which is the #1 probably think tank for string theory in the world. Okay, excessive media, and Mr. Maldacena works there. Okay, excessive media attention and funding of this one particular mainstream endeavor, which he considers speculative, risks overwhelming public faith in the freedom of scientific research. He's worried that all these guys are going to take over, or like someone said, you know, the old theories die when their proponents die, and the new generation invents new theories. Okay, and they don't follow their professors, and it's like a massive movement and a grassroots movement. And the final person I'm going to mention here, and it's this lady, and her name is Sabine Hossenfelder, and she writes a book, Lost in Math. And she's a research fellow specializing in quantum gravity and modifications to the general theory of relativity at Frankfurt Institute of Advanced Studies, up here a couple miles north of where I live. And her complaint is there is no observational evidence. Again, all these people have similar arguments. An area starved of data. That's what she thinks of string theory. And how can non-empirical arguments increase confidence in a theory? And again, I have a problem with that as well, with what she's saying, because empiricism, you cannot empiricize the mediator of light, gravity, or magnetism. You cannot touch or see. The only way to approach the problem is visualizing. In order to visualize, what can you visualize? You need to visualize objects. You can't do physics without an object, so you need to imagine how Mother Nature is doing her work. For this, you need no mathematics, equations whatsoever. Mother Nature does not use equations, she uses objects. And she doesn't move concepts around like all these people. She moves objects. Some of those objects are invisible and intangible, like the mediator of light and gravity and magnetism, etc. And so you're not going to discover them by going to the lab. You're not going to discover them through see and touch, through an experiment. The only way is to sit back, drink a beer, visualize the mechanism. For that, you need objects. You need something, some structure, some entity. Okay. Okay, and the reason I mentioned this lady, I'll be talking about her in the next class, okay, in the next lecture.